So now let's look at the actual experimental result. Now we'll probably just focus on this case, the case where this is really a stress test, where we're not doing anything, everybody is tightly looped, so the delay is 0. We don't give them any chance to wait. They just come in and try to get the lock. So you have lots of waiters, waiting threads, and let's see how bad it is. We kind of already know what they look like. Okay, for instance, test and set. We know that that's better than simple test and set, which is horrible. But still, every time someone releases the lock, in this case, if we have 15 processors, what do you think? Well, 14 of them are waiting. So everyone who releases the lock, 14 of them will be invalidated, and they all go in to load the data. And if this is a perfectly fair system in terms of who gets to use the bus, let's say, then it's actually very bad, because everybody will get a 0 and everybody then proceeds to do a test and set. So we will see that. And really the interesting thing might be the new ones. Okay, so let me clear this up. Okay, here's all the result. You can kind of see the color. There used to be, I don't know why, on my iPad the legends are gone, so you have to guess a little bit. The thinner line is ticket, that's the red, so this is ticket. This is the thicker line is ticket with proportional backoff. Array based is the blue, and the two black you can kind of guess too. With exponential backoff, it's better over here, but it's still going up. The more people there are, the more likely you have conflict. So the array based, remember, well, maybe we'll start with the ticket based. So in fact, it's a pretty poor solution when you look at it. This is a contrived example, of course, but why? Why is it going up so badly? Well, on the release side, this is not very different from test and set. Okay, so again, remember what happens. The thread finishing the critical section will increase the number that says currently serving, and everybody else would get an invalidation, and they will go back, load the thing just to compare. So this is creating a lot of traffic on the bus. Okay, so it's growing up. That's actually kind of a surprise. So what you have to do is to not rush back and read. So you back off a little bit. You think your ticket number is too far from what's currently serving, don't bother reading the current serving. So that turns out to be fine. If you use array base, that's very nice. It's flat. Both these solutions did what they were supposed to do, solve the problem. But you see, ticket log, all three variants, whether the wake up is array based or it's a proportional back off to check or just plain check, all three versions have a pretty high overhead. You can see no matter what, they from 1 to 2 processor, they all grow up a lot. The benefit is that they stay, or at least the two slightly optimized version, they kind of stay flat. And as you have more and more processors, so this is where you can get the benefit. Okay, so the idea is not that the more sophisticated logs will always be better. They're sophisticated for a reason. They're sophisticated in handling high contentions. Okay, so they don't really scale. So they really scale very well, but they don't really have a very good sort of low contention time. The other thing to mention is perhaps if we can get back, that's probably a lot of, even though this looks kind of bad, it's high, but the scale wasn't the same as what we were using before. Take a look at this is 7. If we go back I think it was here, right? Here, when we were using test and set, nothing. This line over here, this is line over here, you can see as we go to 15, the scale is much higher. Okay, so this is not a good solution. These ones that we have now, even though they still have some scaling issues, many of them, in general, they're lower than the terrible test and set. But yes, they all have this trade-off that at low contention point, there seems to be an overhead. So that's the key point, okay? And there's some detailed artifactual issue about these load link store conditional. That's really not that important. So we're gonna switch gear to say, just here are some possible optimizations or different ways of implementing logs. That's about it. There are other logs possibly, but let's switch gear and see what else you can have. These other logs that you have, you may put in software queues. So whoever is going to be the next, why don't you spin on a predetermined location? These type of solutions are actually more useful when you don't even have cache coherence, when you have distributed system, when you still need synchronization, critical sections, and logs. And at that point, you don't even have the option of spinning on a global variable. You have to spin on some local variable. So if you organize these things well, then you're not spinning on a remote variable that you have to go there to read something. So now we're going to talk about a different type of primitives, and that's called barrier. A barrier is rather straightforward, right? So the idea was we are not allowing any thread to proceed until everybody's there. And that's useful when your work is being divided into different chunks, and chunk 1 has to be done before you can start on chunk 2 due to the data dependence of existing in the code. So the basic barrier is actually straightforward, because all we got to do is to increment the counter. Okay, so you have some counter to record how many nodes or how many threads have arrived at the counter, and if it matches the total that you're expecting, then we can go. It's really just that. But the increment itself needs to be in a critical section, which is why we have lock and unlock. And now we don't care about the implementation. Okay, so we just assume this is being implemented by whatever. It can be ticket lock, can be a array-based implementation, or simply a test, then test and set. So you lock the barrier, and then you increment the counter, and if it hasn't reached the total number, if we haven't reached how many processors are supposed to increment, are supposed to arrive to barrier, then we simply wait. Okay, so let's go through this a little bit more. You may have multiple barriers, so the library routine would base on the barrier data structure and how many processors. So everybody would be issuing this in the same group. We would go to the same barrier name, say there are 16 of us, we want to have a barrier. Okay, so if the barrier, if the number of thread hasn't reached predetermined number, the flag is not going to be 1, and you're going to spin wait until it becomes 1. Okay, so if you come in and the total number of threads is not what you expect, in the end, this is what you do. You wait. Okay? But if you happen to be, if the counter is 0, the first one to arrive, you may want to make sure the flag is set to 0. Why? This kind of barrier might be used in a loop. So every iteration, we do a barrier before we move on to the next iteration. So the first arriver, if your counter, if you arrive in the critical section, you'll find out you're the 0th arriver. You set the flag to 0 to clean up, and then you increment the counter, which is done here. Then you release the lock, and now you know you have this my count. You know how many threads have reached, and if it's not P, then you say okay. Then if it's not P, you execute the else. You simply spin on the flag. Someone else is going to set the flag to 1 to allow you to go. Okay. And the last thread to arrive, if this happens to be P, sorry, you clear the counter for the next iteration in preparation for the next iteration, and you set the flag to 1 to say, hey, everybody, we can go now. Okay, that sounds straightforward. So what's the problem with this algorithm? Now pause the video and think about it. Well, there are actually two kinds of problems. The one that I was going to focus on is obviously the performance, just like the log. We have all these unnecessary invalidations and bus activities, if you wish, that slows down everybody, and that's what we were going to focus on. But sometimes some people heard about the problem of the sense reversing barrier, some didn't. In past offerings, it seems like many people don't remember or haven't been introduced to the concept of the sense reversing barrier. There's actually a correctness issue with the code. See if you can spot that. If you know what I'm talking about, you know what is sense reversing, fine. Yeah, you might want to skip the next couple of minutes in the video. I'm explaining that. If you haven't, look at this, stare at this, and see if you can find a correctness issue, that this doesn't work. We will have problems. And I'll give you a hint. Look what we are doing all here, right? Setting the counter to 0, setting the flag to 0, and setting the counter for 0. Why? We're preparing for the next iteration. Okay, so again, the barrier might be used multiple times in a loop. Think about that situation and what can happen. Pause the video. You may find it very interesting to do that. So let's look at the problem with sense reversing. It's kind of used in this way. We have a loop, we go through a lot of iterations, and then we're going to do step I, and then step I plus 1, and so on. And before the job is completely done for step I, we're not allowed to do step I plus 1. And that's why we need to do a barrier. Of course, I didn't put in the barrier name and the number of processors, but that you get the idea. Okay, so this is some kind of high-level synchronicity for the different threads. And you can kind of plug in the code, even though when we put a barrier there, we hide, it's a black box. But really what's happening is, okay, we have a lock after doing step 1, step I, you really have a log, check to see if it's finished, and increment this count by 1, and have this flag called proceed. If you're not the same as the total, the proceed is going to be the variable that you spin on until someone releases you until the last thread to arrive, right? That's the code. What's the problem? The solution to the problem is called the sense reversing barrier, but really the problem is this, that the proceed is set to 1 over here by the last thread to arrive. Okay, but it's set to 0 by the next thread to arrive at the next barrier, but the first thread to arrive at the next barrier. And we don't know, just by looking at the code, there is no reason to believe that this is going to take a long time. Okay, again, this is the last iteration, sorry, the last thread to arrive at this iteration. Okay, the last thread to arrive at this iteration, iteration I, versus the first thread to arrive at the next iteration I plus 1. So this time difference is what we're talking about. It may be extremely small, in which case proceed may be set to 1 and immediately reset to 0 before everybody else got a chance to see it. And I'll use an exaggerated analogy for that. Okay, what is this? This is a town with 3 intersections, if you wish, and it has a traffic light. And the traffic light is very weird. It's red, meaning nobody can proceed, but it will turn green when the last car arrives at the intersection. Okay, so again, in this animation, you see when the last thread arrives, light turns green, everybody can proceed. But pay attention here. The same light has to be reset back to red when the first thread or the first car arrives at the next interval. You see there? And then change. Okay? So let's imagine the intersection. Now, I don't know if you drive, but a lot of drivers that I saw on the road somehow couldn't put their phone down. So let's say the light turned green and you're reading your phone. What happens? Okay, you're a little slow in starting off. But what if this happens really fast? Okay, what if one car, he's probably driving a Tesla, zooms through the intersection and arrives at the next intersection? Remember what happens then? The traffic light is set to red when he arrives at the next section. And when that happens, and you, the slowpoke over here, looks up from your phone, and you're just looking for this variable, right? This variable is 0 or it's red. You say, okay, I have to wait. Now we're in deadlock because you're not going to proceed. And since you're not going to proceed to the next iteration is never going to reach the number of threads that were expected. So we have a deadlock. Now, of course, if I put it in this sort of analogy, you'd say that's ridiculous. We don't have one traffic light in the whole town. We have one traffic light per intersection. So that would solve the problem, right? It would be like this. Okay, that's a red, that's a green light, and that is just a green light. It's done. It's a kind of a single-use green light, but okay, whoever arrives, this change. So if someone arrives very fast at the next one, it doesn't matter. This green light remains green. Okay, so this will solve the problem. But if you go back to the data structure and you say, what am I supposed to do? Well, you will see that we need these different binary variables, not just one flag. We need one for each intersection or one for each iteration, which is doable, of course, but it's ugly. We need an array, if I may, right? We have this flag over here. Now, one flag is not going to be enough. We need a flag array, and that's indexed by the iteration count. So if I'm going to iterate for 1,000,000 iterations, I need 1,000,000 flags. Now, of course, you say we don't need that. What is another way of solving the problem? We can use an integer to count, to say which iteration you're allowed to go through, right? The analogy here is a little bit awkward, but that's in real world. Just to go with it, it's sort of like we're still going with one variable, but it's the level that's changing. That's not just binary, it keeps on going. So, okay, it's red at the very beginning, but the minute The last thread arrives, becomes level 1, which means you can go past to iteration 1, no longer iteration 0, and then when someone arrives last, we keep on increasing this and so on and so forth. Okay, so this will again not have the problem of deadlock. Okay, so why do people propose this thing called sense reversing? It's, I don't know, someone trying to be very cute. So the code that I was proposing would be something like that. Okay, so you come in and you increment the count. Of course, this is all in your critical section. You lock it, you increment the count, and then if the count reached total, okay, and you're gonna reset the count for the next iteration just like before, and now you're gonna indicate to say now this global what we can do is going to be incremented by 1. Okay, and everybody else simply spin until the global iteration matches your local iteration. So if you're here, when you arrive, when you're done, you say I'm done with iteration 4, but the global iteration might still be 3, and the last thread will make it 4, hence the condition would satisfy, and you just go through. That's it. That would solve the problem. And it's not sense reversing. So why is it sense reversing? Well, how many different levels of this variable do we really need? Okay, it turns out we don't have to have many levels. So we can reuse, we can wrap around the counter. When the global iteration reaches 10, I don't know, maybe we can set back to 0. So that works. We just need some maximum amount of level to disambiguate. Okay, but how many levels do you need? 2. Your only confusion is really between the previous iteration and this next iteration. That's it. So max is 2. If you're mod 2, and what are you doing? You're just reversing the sense from 0 to 1, from 1 to 0. So this is what you're doing. So you have a local iteration, or it's no longer an iteration, but a flag or whatever you want to call it, an indicator. So every time you flip it, and that's hence the name sense reversing barrier. So you get that, and that's sort of the cuteness of it. Now, okay, so what is the real problem? The real problem here is still, first of all, we have this lock. If everybody arrives at the same time, okay, problem. Right? Everybody wants to grab the lock to increment, the same lock, to increment the count, and so on. And this actually happens in ideal case. What's ideal case? Ideal case is I have perfect load balance. Everybody arrives at the barrier at about the same time. We have the same workload. Otherwise, the entire iteration, the speed of the entire iteration is determined by the slowest thread, right? So in the good case, I have actually the worst case in terms of the lock. So how can we solve that problem? One solution being proposed is to decentralize. Let's not all go to the same lock. And here we use the notion of a flat barrier versus a more hierarchical one. What is a flat barrier? That means every node, node 1, node 2, node 3, so on, all want to grab one lock and update it. So when they arrive at the same time, there's more possible contention. How about we split them up? So the upper 4 threads would barrier over here, the lower 4 threads would barrier over here, and when both are done, then they communicate again. So you turn that into some sort of a combining tree. So at each level, you don't need to have so many threads using the same lock. So you see, I don't have contention between these two nodes. They're grabbing different locks. Okay, so then there is more parallelism to proceed. Okay, so there may be a little bit of delay because in a, let's say, not load balance situation, and then it's probably fine over here. Everybody comes and change the lock, grab the lock and change the counter and proceed afterwards. The last guy who arrives will grab the lock without contention, change it, release everybody, and that's fine. And in this case, the last guy will finish the barrier in his own node, and that node has to keep on going until it reaches the root of the tree, which then back propagate down in some way, and this can increase latency. So you see, it's never kind of a real optimization. It's always a trade-off. Makes some cases better and some cases less good. Here's a simplified pseudocode for that. Okay, so your barrier is going to be recursive. Okay, why? Because it's basically this. I have some node and I'm going to do a barrier. When I'm done, now I'm actually starting another barrier, which is a level up. And so on and so forth until I reach the root, and then the propagation is also part of the recursion. So when I arrive, of course, we said we use lock to increment the count, but if you support primitives such as fetch and increment, you can do that too. Okay, so suppose we use a k-array combining tree, meaning at each node we have k threads to barrier, to reach the barrier. So we'll increment that, and of course we're checking to see if it reached k-1. That means after counting ourselves, our all k would be fine. So here is what happens if you're the last node within the curly bracket. But if you're not the last node, then you go back to spinning. Okay. So if you are the last node, last thread to arrive at the node, then you're done. But only for this level. Okay? And you're supposed to participate in the next level. So if you don't have a parent and this is root, then you're done. But if you are, you recursively call the barrier thread again, or library call again to say, okay, now it's just at a different node. Okay, but if you are the last node, then you simply set my node flag to 1 and releases everybody. Now I'm not doing the sense reversing. Okay, for simplicity, I got rid of the sense reversing code. So yes, this would be wrong, but it's easier to write the general idea rather than the specific code that is bulletproof. So if we do this, and there are lots of nodes to have barrier, and they tend to have contention, and now we parallelize this contention process. We have different nodes. Okay, only the last node is the global node, but then the degree of contention is reduced. Think about, suppose I have 64 threads and I have an 8-way barrier, then I would have a 2-level tree. But the 8 non-leaf node, the 8 last level of branch would only have a contention of degree 8. Okay, so yes, it's going to take some time, but it's better than 64x. So the 8 different branches are doing barrier simultaneously on different log variables, so you're fine. Okay, and so yes, I may increase latency in the uncontented situation, but in the contented situation, I'm a lot faster because of the parallelism. Now, if we sort of, there's a specific case of this combining tree idea called the tournament barrier, and it's just a minor optimization or a minor deviation from the general idea. Here, what we're showing is whoever participates to the next node, this is the last guy to arrive. But if we predetermine among the 8 nodes, number 3 is going to be the guy who participates in the next node, and that's there's some benefit to that, especially if we can pre-allocate where we spin these variables. So there's one version of that does that, and that's called a barrier, a tournament barrier. No big deal. Really, the idea is that using the tree. Okay, so we see that the barrier is not that much more difficult. It really uses critical section, perhaps a very small critical section. So a lot of this general problem or general issue is about how to make lock more efficient. And we're not done about the problem of locks. It's beyond just the performance issue that we described in the case that we show here. There's a lot of contention, then it doesn't scale very well, the performance is poor. It's beyond that. There are even more pernicious problem, if you wish. And here is a list, an incomplete one, of the gripes people have about lock. So you can have a deadlock, right? There's critical section. I want to go into critical section, so I need to wait for a lock. But maybe inside the lock, I need some other resources. So I need to grab some other lock. And this can form a cycle of dependence relationship. And then we have our deadlock. In fact, when I was in grad school, there was one Martian rover that was sent by NASA, and it got stuck on Mars. And after some furious debugging on planet Earth, we realized that the exact problem happened in this case. There is even a name for it. It's called priority inversion. So what happens? It's that the higher priority thread is waiting on a lock, which is now held by a lower priority thread. And the lower priority thread was never even allowed to execute because there is a higher priority thread available. But the higher priority thread, of course, is just spinning. It's not doing anything. So now we have this thing that's called a priority inversion. The higher priority thread is waiting for the lower priority. Now, of course, this problem has been known for a while. The solution is fairly straightforward. So if a higher priority, if a lock is being held by a lower priority, by a thread, but it's being weighted, if that's even a word, if a higher priority thread waits for that lock, then whoever owns that lock gets a higher priority. Okay, it gets the same priority as the guy waiting. That's called priority inheritance. They changed the code. Fortunately, the mechanism allows the OS to be uploaded, and lo and behold, the Martian rover would reset and then continue without problem. So that's problem. Okay, there are solutions, but if you're not careful, the problem will get you stuck on a remote planet. And it's also not naturally composable. What does that mean? So suppose I want to move a node from one linked list to another. Moving linked list is usually, suppose it's a parallel data structure. There are multiple threads maybe doing that. You know that you need a atomic block, a critical section to insert a node, because you need to manipulate a whole bunch of pointers. They need to be done together as an atomic block. That this applies both to delete and to insertion. So let's say I already have my code written for insertion and for deletion, and they are all by themselves atomic, but I cannot simply put them together to say delete and insert, and then I have an atomic block. Move is atomic. You have to delete it from one place and put it in another, all in one go. So how do I do that? I need another lock, because this is a new critical section. The two previous one that handled each individually for delete and insertion doesn't work. So if I have something that's called a dual atomic, blah, everything, that's great. That's composable. I can have a dual atomic with components inside that each has their own dual atomic, and it will still work. So it's not naturally composable, and we'd like it to be somewhat composable. What else? Something called convoy. So the idea is, well, you know, convoy on highway, a bunch of truck going together. So the togetherness is the issue here. Suppose, so you have each individual threads. These threads are operating system controlled threads. At some point, the OS may come in and context switch out a thread in order to be fair to other threads that's waiting. Okay. So, but what if your thread is holding a lock at the moment? He's in the critical section, but just as he entered the critical section, the OS comes in, swapped him out. Well, if there are other threads waiting for it, they're effectively being swapped out, even though they might be spinning on something, but no, they're not making forward progress because the lock is not going to be available. So you have this, taking out one thread, you're effectively taking out a whole bunch of them. And worst case would be that they are actually actively spinning on something rather than yielding their processor time for some thread that can make real forward progress. Also, how many locks do you have? Okay, there's a very hard problem to decide the ideal granularity of locks. Because on the one hand, you can have one big lock, no matter which critical section in this whole entire program. Anybody who wants critical section, just grab the lock. So that's easy. I don't have to worry about the exact lock variable. And that's the other thing. I have a critical section. I have 5 different places that I may touch a critical data structure. They have to use the right lock. If your code had a typo, you were acquiring a different lock, and then you're not preventing or providing the right exclusion, mutual exclusion. So if you have a lot of smaller locks, you get the chance of writing, more chance to make bugs. So if you have this one big the lock, well, that's great. Nobody can write that code wrong. Okay? It's very easy to grab the lock, go into your critical section, then you're done. But then what's the problem? Then you have false mutual exclusion. I want to execute code section A, you want to execute code section B. Both are critical sections, but they're doing different things. And we don't have to wait each other. If I have one coarse grain block, I have these unnecessary wait. But if I chop down all these critical sections into their fine grain locks, and I have this mess to deal with, and I can have all sorts of problems. So over the time, a lot of people come up with all these complaints about lock as a synchronization variable, as a synchronization mechanism. Is terrible. And we'd like to do something about it. And that's where we're going to have a very, very brief look about that argument. Despite all these complaints about locks, that's still what we're using today as the main way of achieving coordination between different threads. But yes, there are other ways, and we're going to look at them so at least you get an idea what these mechanisms are.